Hi. I'm trying to talk today about immersive applications, or the immersive experience you can have with applications. The experience we have with applications can differ greatly. Like, we can enjoy using an application, we can feel supported by it, or we can feel indifferent about it, not really recognize its existence much, or we can feel frustrated. It can be a real plight being reliant on an application if you don't enjoy using it. Companies these days do a lot to ensure that you like using the application. But what exactly does that entail? And how can we aid Rust developers to do the same? And a lot of this is UI, and we've heard a lot yesterday and today about UI development, and I want to skip that today. I want to put UI aside and look at everything else that an application can do to make it enjoyable and help us use the application. So let's look beyond UI and look at a few of the applications that probably every one of you knows. We could look at one of these and see what they do right, what they do wrong, and probably a lot of these, because they are big applications, they do a lot of the things right. They probably also do some things wrong for business reasons very often, but I don't want to look at them. I want to introduce you to something that you probably don't know and take you on a short journey with it. I want to introduce you to this. This is called Deutsche Bahn Navigator. It's an application that translates to German railway navigation application. And to understand this, I have to explain a bit about my background. I live in the German countryside, and we Germans, we love trains. We build trains everywhere. We build train tracks everywhere, and I really mean it. If you look at the German countryside, this is a completely reasonable setup, right? You have a small town, 12 people live there. They need a way to commute. We built them a train station. They need to get out of that town to get to work. And we really expect this kind of setup when we plan our journeys. When we want to go to the countryside, we expect to be able to get there via train. And trains are really ubiquitous, but it's not just that we build train stations everywhere. We also enjoy improving the train rides and improving the train stations we have. So we have also huge projects that try to take existing train stations, like in this city, which is a German bigger city called Stuttgart. They had a big train station in the center of the city, which just tore the city apart because it's a huge bed of train tracks that's hard to cross, and it was a terminal station, so trains had to enter the city and out again, lost a lot of time. So what did we do instead? We dug underneath the city. We built a new train station just underneath this existing metropolis, and then decided to rip out the train station afterwards. So all this space in the city center got free. We could build new homes, new parks, and enjoy all that free new space. So long story short, we Germans, we really like trains, and we enjoy making it better. But there's one problem with this. And this is the company, no, the institution in Germany that operates all trains, called Deutsche Bahn, or German Railway Company. And it's a bit controversial in Germany, because we Germans, we desire to be on time. And this company gets a bit in the way, because it's really hard to keep train schedules, and they have a history of having a lot of delayed trains. And it's a widespread opinion, and you will hear Germans complain a lot about delayed trains. And it's not that we really hate the company. No, it's more that deep inside we feel a bit embarrassed. We're kind of proud sometimes that people think that Germans are always on time or take this seriously, and they kind of get in the way. And if tourists see that and take the trains and judge us by this, we're kind of embarrassed of that. And the worst thing that can happen is that you visit the neighboring France and tell us Germans that their TGV was on time. So we Germans, we don't get along with this company very well. But yet comes along this application that I wanted to introduce you to. And the thing is, even though The setup was not good, even though like most Germans did not like that company. This app is good. The Germans love it. Almost everyone uses it. It's the best app to deal with the train system in Germany. So how did that happen? What did they do right? And that's what I want to look at. So this is what the application looks like. It does not do much. Like, there's not much you can do when you're dealing with trains, right? You want to have a screen where you can plan your tracks, plan your rides, book a ticket, and then the other two is when you're on your journey. How do you like show the conductor your ticket? How do you know whether you're on time, when you have to change trains, and so on? And this looks reasonable. It's not a beauty, but it's far from ugly either, right? But we said we want to put UI aside. So what else does this application do that makes it nice to use? On the left side, for the trip planner, like, we start with the very simple things. When you're starting a trip, you have a starting location, you have a destination location, you have a departure time or an arrival time, and that's what you search by. And with one click on that application, or one touch, you can get the current time as the starting time. Very simple, makes it a lot easier. If you wouldn't have that, you would have to scroll through the time and click on the right time that is currently on, even check your watch. The other thing is, with one click, you get the current location as the departure location. And it will find the nearest station to your departure, to your current location, and use that. And also, that means on a mobile phone, you have to type in like only half the stations that you want, that you need for that search. But even then, if you're looking for the destination location and you type something in, it uses kind of a smart search. Rather than giving you the best matching stations based on like a verbatim match, it tries to give you, for instance, the biggest stations, list the biggest stations first, because it's most likely that you're going there. And lastly, once you found your connection and you want to pay for a ticket, it uses the payment options stored on the device to immediately give you an instant checkout without registering. You can do all that, but it can also use just the things provided by your platform. And this makes it really, really much nicer than a lot of the alternatives. But once you got your ticket and you're on your ride, the other two screens come into play. So what you always have to do is, like, a conductor comes along and you need to show them your ticket. What it does, it shows you the QR code, rightly scaled up. The conductor can scan it. That will ensure you have a valid ticket and it's okay. And it's not like you download a PDF, have to scale it and move it to the right location on your screen. No, it just shows it in the right size. And with one tap on the QR code, it will lighten up the display for 10 seconds to make sure that the scanners actually work on your phone. Which is, like, I've very often seen people on trains that had to manually increase their screen brightness just to ensure that these scanners work. Inevitably, when you will get delayed, the application allows you with a one click to use your current location, your current time, to tell you all the alternative routes you can use to still reach your destination. It will notify you via rumble of your phone or via sound when you have to switch trains, about delays or about other updates of your journey. And lastly, when you reach your seat in your train, you can avoid all the dance with the QR code by just scanning an NFC tag on your seat to check into your seat. And it will automatically say, okay, you have a ticket for that seat. No conductor has to check your ticket anymore. And these are not big things, right? This is not like these are brand new features, but they make it so much nicer to interact with this application. They avoid, it avoids having to type all this information manually on a mobile phone. And most people don't enjoy that. Like, you might be standing in the rain, you might be having sweaty fingers, you might not enjoy typing on a mobile phone. And all these features avoid this and give you other options to get to the same result. So, long story short, despite being looked down upon, this company produced an app so good, Germans love it. And I would say, if you're an app, you want to be like it. You want to learn from that, and you want to do something similar. I've compiled a list of other things that belong into the same category, or maybe they share the same stuff I already talked about. Just to give you more examples of what you can do to integrate your app with the ecosystem and to improve the experience users have with your application. In particular, integrating with the ecosystem of the platform you're running on is crucial. And this means very often not just dealing with the devices or talking to the device, but also just doing things the right way as it is expected on your platform. In particular, if you're dealing with contacts, use the way contacts are stored off the way the platform does it that you're running on. Don't invent your own lists. If you're dealing with files, use the file manager of the platform. If you're dealing with accounts, use the account system of the platform so it can be shared across multiple apps, so it can be pruned when the device is reset and things like that. For interactivity, don't just rely on screen output and touch input. Use everything else if it makes sense. Use the camera, microphone, and touch screen to get more different ways of input from the user. Use the speaker or a rumble device or a backlight to get more output to the user. And similarly, use peripherals and sensors to get more information from the device, like location and orientation information. For mobile devices, really useful. Use Bluetooth and NFC to make it easy to share information with devices close to you. Use things like automatic SMS verification, where you hook into the SMS system of the device instead of letting your user copy PIN codes that are sent to one app of your device over to the other app. Or react to things like device health information, like the battery status. And lastly, on that list of examples, use storage the right way. Check out how your operating system or how your platform provides long-term and short-term storage. So you put the information you have into the right place, so it's pruned at the right time or preserved at the right time. To summarize all these things, I think well, that's a weird list. That should be 1, 2, 3. To summarize, I think we can take these 3 categories. You should integrate with the OS and ecosystem. You should adjust your decisions to the device you run on. Like if you're running on a desktop device, expect your user to be less hesitant to type. But if you're on a mobile phone, expect your user to be less hesitant to scroll through suggestions. And the third one, make use of sensors and auxiliary devices. So how do we end up doing all that? If you're a developer of an app, what can we do for that? And it's not that you have to jump down to a hardware level to do any of things, because this is not new, right? All these platforms have realized that this is highly useful, that improves your experience. And the native level provides all that. And all of the common platforms, the Win32 API, the macOS or the iOS framework suite, and the Android and Harmony OS SDKs, they all provide you the APIs to do all that. On Linux as well, that's a bit less simple. I've also included the web as a platform, as nowadays it's very often treated as a platform itself, even though it's actually like more of a portable effort in itself. The big problem of all that is they are not written in Rust, right? But we want to do that in Rust. We want to give Rust a first-row seat to do all these things, to have our applications written in Rust, as we just heard yesterday and today. And they are very, very nice solutions to write applications. But we want to enrich these applications with all these features I'm talking about. So I've developed, or like we've developed, a 2-step plan to get there. The first one is we need native Rust support in the platform SDKs. Right? We want Android to support Rust applications as first-level applications alongside Java or Kotlin. We want them to provide their SDK in Rust with native Rust APIs. And then on top of that, we want portable Rust abstractions for all these platform APIs. The big issue here is this is not going to happen. Like it took 10 years, I think, for Android to finally accept Kotlin as a second language. And Kotlin shares almost everything with Java except its syntax. So what can we do in the meantime while we lobby everyone to go that direction? What can we do to still get everyone, well, some similar experience? And I think there's two things to concentrate on. The first one is ensure that we can build Rust on all these platforms with all these that we can build Rust applications on all these platforms and include Rust code in our applications for these platforms. And secondly, that we provide access to raw APIs of these platforms. As soon as we get access to these raw APIs, the ecosystem will be able to pick them up and create everything on top. And that's what we are doing with a project called Osiris, which means operating system interfaces in Rust. We're targeting the most common platforms out there, which probably includes almost all of the common devices. This is under construction. A lot of this is still like a moving target, and we are evaluating which parts we are doing first and which then, and how to get there on each of the different platforms. So what is Osiris doing? The idea behind Osiris is you still have to write your application. We don't do that for you. But if you then take Osiris on top, what you get is a Deutsche Bahn Navigator. You get something that is nice to use. And there are two things that we want to provide you to get there. First of all, we want to provide you access to APIs. So you can use, for instance, battery, geolocation, storage, or time APIs to get access to all this information on a specific device. But secondly, we also provide you the build system to get the final artifacts for the platform that you want to build for. And this is as simple as just typing a cargo extension, cargo Osiris, you specify build, and you specify the platform you want to build for. And this will produce the final artifacts that you can deploy to a platform. So in this example, for instance, it produces an APK, which you can directly deploy to Android using ADB, the Android device bridge, I think. Somehow the enumerations are really not working. The four pillars of the Osiris projects I want to now look more into. And the first one I want to look into is the build system integration. And what exactly it entails and why we want to concentrate on that and what we think is currently lacking. And one important thing that we identified is that it's crucial to use the platform native build system for each platform. So we all have opinions on these build systems, and build systems are very opinionated things. But we believe it's crucial to pull cargo into the existing systems and not vice versa. Yes, we all agree, we love cargo, it's a nice system, and we would love if everybody adopted it, but there are really big issues if we do it the other way around. Like if we would rely on cargo and extend cargo to do everything. And the biggest issue is that third-party integration is required by every application. Like every application uses something that they're provided by a third party, and these things often describe how you can include them in the native build system of the platform. You will have a hard time trying to include them in any custom build system that you use. Secondly, it follows platform recommendations automatically. Like you get the default build flags, you get the linker flags, you get like security considerations, like address, layout randomization, and things like that applied automatically if you use the build system of the platform. And third thing, platform linters are applied automatically. You get information about things you're doing wrong on the platform. And all this stuff is really hard to do, or you have to copy like all this functionality if you try to do it somewhere else. And lastly, it's slightly forward compatible to what happens when we eventually will get first-class Rust support for a platform. And secondly, what you also have to consider whenever you talk about these build systems is integration with the platform's native stores. Because if you're a business, you really want to support them. You want to be compatible with these stores, and these stores have quite restrictive policies. There are things you can do on a platform that the platform store does not allow you to distribute an application if you're doing that. And this is not like, you can avoid these stores and ship your applications via other ways, but you will run into problems, and that is not just the problem of that it becomes hard to install and update your app. No, it also becomes hard to support closed company setups where companies have like remotely managed devices, or they control these vanilla images that they deploy to their employee devices. Because they very often rely on functionality of these stores where you specify which apps of a store are installed on a device. By using the build system of each platform, we make it much easier to get the linters to warn us about things that are not compatible with the native stores. We automatically get the artifacts compiled in the right way. So we believe this is crucial. We need to provide a way to allow developers to use the platform native build systems to build their Rust applications for a platform. The second thing to talk about is native API access and cross-platform APIs. How do we give that to Rust developers? And there again, we believe that raw first, abstractions second is a crucial rule. We want to unblock early adopters. We want to ensure that everybody gets access to the raw APIs on a given platform. And then, once we have that, we can design more Rusty APIs and make them more ergonomic in Rust. But if we don't concentrate on raw first, it will be really hard. Like if we only provide the Rustified versions, like we will not have the same collaboration, and we can aid contribution and unblock early adopters much better if we just give them raw access and then later on collaborate on how do we do that in Rust. Secondly, platform-specific first, cross-platform second, for almost exactly the same reasons. And also there to keep in mind, if we write platform-specific APIs for half a dozen platforms, it's invaluable experience to write cross-platform APIs, right? So yeah, we believe good native Rust support of the platform-specific APIs drives good cross-platform APIs. And wherever possible, keep the web APIs in mind. They have done a lot of the similar things here, not for all the same APIs, but for some overlap, and we can learn from them greatly. And lastly, we want to always allow modularization via crates.io. We want to maximize collaboration, right? We want to allow everyone to share their ways, their ideas of a cross-platform API or of a Rust abstraction. And we want to prevent reliance on specific baseline crates. And this is very hard to do often because you need specific traits to share across your APIs to use them. But we don't want to prevent people to rely on these things, but we want to allow them to pick and choose. We don't want to say, you have to use that one to use a specific build system or to work on that platform. And before I talk about the last step, I want to say that these things are like, you can use each individually, right? You can use the build system integration without using the native API access or the cross-platform APIs. Or you can use the documentation we provide for each platform without using anything else. And we believe this is really important, and this ties into the last aspect, the Rust platform documentation, because a lot of this effort is documenting how specific things work in Rust and how you can use it and what the ecosystem already provides us. We've talked about the native API access and the raw API access. First, the best thing that can happen for us is what happened with the Windows Rust crate, where Microsoft decided to provide a crate that is pure Rust, that just provides access to the raw system APIs, and they maintain it, and they granted it to us, and the Rust system ecosystem can now create everything on top that they want, right? Microsoft didn't decide in that scenario to just provide access to the high-level APIs or give their own abstractions or a huge SDK. No, they just created one small crate and said everything else on top can be created. So it doesn't mean we all have to copy the efforts. We can just document this is the best way or one recommended way on Windows to get access to the raw APIs. It doesn't mean the Osiris project has to do all that, but we just write it down. We tell you the options. And this is the biggest aspect, I believe, is the documenting all this. And what you have to understand there is that these are the target platforms, and they are hugely different. And not everyone can be knowledgeable in each of these platforms. And they can be very, very different if you have an application. If you just look, for instance, at Windows or Linux Flatpaks, if you start an application there, it will be running in its own process. It will start as an ELF executable or as a PE executable. It will have control over its environment. It will be able to spawn its own threads, have nothing but the C runtime loaded into the application. And very often it has access to the environment. It can access the file system and it can talk to the kernel. Compare that, for instance, to Android, where you are running always in a JVM. You're always subject to whatever the JVM does. And this is you can't access the environment in the same way as you would do on Linux Flatpaks, for instance. And it's really hard then to create an abstraction for applications that can run on all these different platforms and still behave the same way. And that's why we really, really believe documenting what is allowed on each platform and how it works is crucial. And then documenting what works, what can you do on all platforms, and which way will you get the best result. So ultimately, this is what we want to provide you. We already have a lot of existing UI frameworks, we have application frameworks, a lot of things. You can write applications in Rust. We want to ensure that this becomes nice and that the result becomes as good as possible. I've prepared some more details about the problems you're having to deal with, but I first wanted to give you a chance to just ask a question yourself. So maybe we can just discuss other things. Otherwise, I will just proceed with some of the problems we are facing and our proposed solutions.
Hi, thanks for the talk. I have a question about how this effort fits in with existing crates that already have platform abstractions over device features. For instance, there are crates that allow you to access Bluetooth on different platforms. Would this be a replacement, or would this be something that sits alongside those? How does that work exactly, or how do you think that will work?
Yeah, I think it's similar to for instance, the Windows crate that I talked about. We try very often to just use whatever's already there for a platform. Like for Java, for instance, there's the JNI sys crate, which allows you to interact with the JNI. Sometimes some of these crates have issues that don't allow you to deploy them to all these systems, so we have to look into alternatives. But the idea, again, is to allow using all of them together. Not to mandate one specific crate, but to actually say, if you're using that thing, this is how you can do it. Once you start using abstractions, of course, these pick and choose. But the good thing about these platforms is they do have a stable API, right? And in most cases, stable API as well. So there is one boundary where even if you use multiple different crates to access the raw system, they are inevitably compatible, as long as they expose the raw types of the platform. So as an example, on Android, even if you use different JNI crates, if your abstraction allows you to expose the underlying pointer to the JNI type, you can use them and import them into another abstraction and get compatibility that way.
Full abstraction? Like in man hours or money required to spend on this?
So this project, this started like a few months ago. So a lot of this is discussing where we want to go and what we want to do. And the hardest, the abstractions are actually not the biggest problem because, as I said, the web has done a lot of similar things. And picking just whatever the web did and doing something similar in a native way solves the issue of designing the abstraction. The web abstractions have issues, but for instance, VASI and the GOSIM runtime, they have done something similar, and they also not always, but often has done copied from the web APIs. I would say that the biggest effort is trying to figure out how to get the raw platform APIs that work for all use cases. Because a lot of the existing ones, somebody dumped them out there and figured out, yeah, this is how you can run an application on iOS. But then you look into it and you can't use var args with it, or you can't use something specific with it, or they only work on a specific architecture. And trying to figure out, this is the set of platforms we do and so on. I think this is the biggest effort. And this really depends on how far do we want to go, which are the platforms we want to support. To quantify, I don't know in what unit, but
like a team of 10, a team of 20, a year, 2 years, 10 years.
We want to be able, next year, to get something where you can actually use these APIs. But we start with things like, for instance, time and storage, because most people use them, and they're the most trivial ones. But once you get into things like camera, this gets dicey because it interacts with a rendering pipeline where you want to shortcut things and you can't just always copy frames out and in and things like that. And there you really need to interact with the UI frameworks. So I don't know. I could say, oh, you can do that in 2 months, but then you stumble up across some roadblocks and suddenly it takes 2 years. So, yeah. I have a few more slides just to give some examples of the issues that we want to solve, which are very often Rust ecosystem issues that everyone runs to once you start writing such applications. And one of the things, for instance, is non-Rust source bundling. A lot of the platforms use languages other than Rust, which require you to write some code, some stubs in a language other than Rust, and you can't get away with it just writing everything in Rust. One example is, for instance, Android. This is just one of the most obscure platforms because it just uses the JVM. On Android, what you can do is you can use ChainI to use the Java native interface to write Rust, native Rust code, which then interacts with the JVM. But the only thing you can do there is you can specify Java methods that you want to implement in native code. But it means you somehow need to tell the JVM this is a Java method which is annotated as native method. And this class that has this annotation somehow needs to get into the JVM. So how do we do that? How do we create small crates that provide one of these features and allow them to ship Java code? One of the best solutions would be to rely on Java, compile once, run everywhere, right? Problem is, Android does not comply to that. You can't use that on Android because Android does not use the Java class files. So the other option, what the ecosystem is already doing, is they write build.rs scripts where you provide an environment variable that points to a directory and say, hey, I'm compiling this crate and all its dependencies, and here's my environment variable that I point to this directory. Please copy all your Java files here. And then you compile it, and they will extract all their files, place them there, and then you can use them to include them in your build. But this is kind of nasty because it's non-declarative, right? You can't know up front which files will you end up having to compile. You can't inspect them. And it's really not something you would choose. And the route that we took and that we want to kind of mandate is to allow crates to specify in their cargo.toml metadata to say, this is a directory where you can, where we have Java files. This is a directory where we have Kotlin files, and these are bundled together with your crate, and you can push them to crates.io, and anybody who's compiling your crate can then say, write, the metadata already tells us about this. This requires agreement on the formatting to use in the package metadata. Like you can already specify arbitrary information in cargo.toml in the package metadata section, but you kind of need to agree so the build systems, like all the crates can share the same format. Another problem that we're currently facing is what exactly is, like, how do you say this is my Rust application? Preferably we would say you have a cargo.toml and you say, run cargo there, it will compile the artifacts and it will tell you, like it will give you the application and then do whatever you have to do to create your final artifacts for a platform. The problem here is, first of all, we want to collect all the metadata about the crates that are involved, like pull in all the dependencies, get all that information out, because all these dependencies might have information about, as we just said, non-Rust sources that we have to pull into the build. They might specify permissions that are required to put into your manifest. Like if a crate implements a camera device, you have to put in permissions to your final artifact that says this application needs camera permission. And there are more examples. And the biggest problem is just pointing to a cargo.toml file is often not enough, because that toml might be a virtual manifest. It might be multiple packages. And it doesn't really tell you which one implements the application, which ones are supportive crates, what exactly do you need. So it's a lot of information just required in the build system to tell you what exactly you want to compile. And then you need to, luckily we have cargo metadata to get all that information out of cargo.toml, but then you have to parse this entire dump of information to pick exactly the things out you want to use, because very often it points to a virtual manifest, and there are a lot of packages, but you're only interested in a specific package and its dependencies. And then suddenly you have to parse all the dependency information yourself, resolve all the dependencies, and get all that information back. It's a bit cumbersome, and not like, I don't have a real solution here, but it would be nice if there would be a more, like an easier way to say, this is an application, and we point to that cargo.toml, and that's it. And the other problem with that is it doesn't tell you what the artifacts are that it produces. Like once you build via cargo, it will tell you with metadata, with JSON metadata, these are the artifacts I put into the target directory. But it doesn't tell you up front. You can guess them, but it feels kind of wrong to guess like which are the things that are produced, especially once cargo gains more functionality to allow you to compile dynamic options and link between them once we get, for instance, a stable ABI. Yeah, this is kind of, it's not really a technical problem, but more like a design decision problem. What do people agree on? What do people want to specify there? And now to go one level down to the actual application, once you keep running on a system, the different platforms give you different control over the main loop, different control about the threads that are executed for you, the environment you're executed in. On some systems, like for instance most Linux package systems, but also on Windows, you're dumped into a process, you get full control over the main loop, you can run the loop yourself, everything is usually fine because you can decide yourself what you want to do. But on other systems, for instance, like Android, you have more like this callback system where Android manages the main loop for you. And this is often hidden behind you because the UI toolkits, they found a way to abstract over that in their different platforms. But they don't expose it to you, and that can lead to problems because they might design things in a way that are not compatible to all system APIs. So for instance, what a lot of existing solutions do on Android is they spawn a separate thread and run their Rust main loop in that separate thread and then invoke all your callbacks in that separate thread. But this runs into problems when you have APIs that can only be dispatched on the main thread. This also runs into problems once you start sharing like these separate thread loops often send commands back to the main loop to get like interaction with the main loop. But this runs into problems with ordering once you have commands you directly send out via system calls and commands you send up back to the main loop because they get misordered unless you have like a synchronous loop back, which usually they don't. And these sort of things are often very much hidden, but once we start having an ecosystem where everybody can provide things and you can plug and play, these need to be documented and these need to be exposed. And very often you need a way to get the raw handle of the underlying platform. And this ties into the next problem, which is context. Once you start sharing a crate that, for instance, provides your geolocation, that geolocation constructor that needs access very likely to a context provided by the platform. And very often the UI tools are the ones that have control over that because they have their own way of starting up and getting integration to the system. But they all now need to expose this kind of information in a platform-specific way because it's really hard to abstract over that. But they don't do in the same way. And I don't want to judge them. I mean, it's often easy not to do that because, I mean, either you don't know other people need access or you don't know how to expose this information. But it's really crucial that you do because everybody else needs this to create their context objects as well. And we've touched before on that, on your question. The nice solution here is that the underlying platforms are all ABI stable. So as long as we can provide like these void pointer constructors where you say, just give me the pointer to the context, it has to be this and this pointer. It's an untyped thing provided to me, but it will work. That's a nice thing. This allows us to share between all these platforms. But it also requires everyone to expose them and to give you access to these raw pointers. The last one I had was on some other, like looking to other platforms, but Jonathan already did that very well, so I will skip that part. But I will point you to an Igalia survey. They made a field survey just this year and published it, where they look into these different frameworks and more, especially the one that Jonathan also mentioned, and compare them and tell you how do they solve these problems. And very often, like, they don't. They all really struggle with this problem, with trying to provide all these other abstractions for these platform APIs. And that's why I really believe we can make Rust better there and, well, help the ecosystem actually just shape the future there. That's it. Thank you.